This video is looking at a Carnot cycle where we have a controlled volume. Here we have a controlled volume, so our DET, or our controlled volume, dt, is equal to 0. And our mass of our controlled volume is also equal to 0. We're going to assume as long as this is equal to 0 if it's at steady state. Not always, just because it's controlled volume. This is because we're at steady state. Those are equal to 0. All right? We're going to look at various ways to solve this. So our first law of, we have state 1 to state 2, where we're going through a turbine. That's our adiabatic process. 2 to 3, as you go through the condenser, that is an isotherm. 3 to 4, we're going through a pump that's doing it adiabatically. And 4 back to 1, we are at another isotherm, but we're at the higher temperature where the heat is being put into the boiler. So if we think of our first law of thermo, we're looking at our heat, our work, and let's go back to our CVDT. And this is all the sum of the, right, is equal to 0. This is the sum at the inlet minus the sum of the masses at the exit. And here we have one inlet, one exit at each stage of our process here. So our mass is 1 is going to equal to mass at 2, which is going to be the mass at 3. And these are all rates, so I have to have that dot. Mass at 4. And I'm just going to call this mass. Okay? So here, since we only have one inlet and one outlet, when we continue our first law, we also have our mass at our inlet times, and the other thing I'm going to assume here is that kinetic energy and potential energy are negligible. And that's HI minus the exit, HI. Since the exit in our inlet in this case are the same, this is going to be 0 is equal to Q W plus in general. So if we're looking at our process from 1 to 2, and that one is adiabatic, right? So we're talking about our turbine, and our Q at this case is 0. So if we're looking at our first law, and this is 1 to 2, our this is Q is 0. So our work here coming out of our turbine is going to be mH1 minus H2. If we're going from state 2 to state 3 through our condenser, that is our isotherm. We're giving off heat there. In this case here, through our condenser from 2 to 3, we are also at a constant pressure. So pressure 2 is also equal to pressure 3, besides T2 is equal to T3, which is Tc. Q minus W plus M going from H2 to H3. Our fluid work is part of our enthalpy. So, but all the other type of work in our controlled volume is 0 for a condenser. And so this is from 2 to 3. And so Q2 to 3, which is our QC, right, is going to be, if I bring this over, then it's H3 minus H2. Take that negative sign through. If we look at process going from 3 to 4, we're adiabatic again. And now this is our pump. So our Q from 3 to 4 is 0. And so if we look at our first law, our Q is 0. And so our work of our pump that's work being put in is equal to the enthalpy from 3 to enthalpy 4. And then our last process from 4 to 1, back to 1, is another isotherm. And that's going to be T4 is equal to T1, which is also our hot temperature. And so this is going through our boiler, happens to be also isobaric, so P4 is equal to P1. And if we look at our first law, here our work is 0. And so then Q41 is equal to, and then I'm going to switch these two around because I put it onto the other side. There. Now, if we want to find terms here, we know that H1, if we're looking at H1, we can see here that H1 is a saturated vapor. So for a saturated vapor, this is Hg. Okay. If we look at if we look at state 4, that's also right here, and that is a saturated liquid right there. So that is equal to HF4, and that is going to be at a particular pressure or temperature. They can give you one of those, and we'll know that what that value will be. Now H3 and 2, we're within that liquid vapor dome, and because of that, we're temperature, pressure are dependent on each other, so we can't know where we are within that dome. We need another property, and sometimes they'll give you the quality, other times they'll give you the specific volume, so then you can find the equality and so forth. But if they give us the quality for that, then we can find H3 because we know HF3 minus the quality. And then that's this special term here, Fg, is already that difference between the vapor and the liquid, saturated vapor and saturated liquid. And then H2 would be the same thing, but we'll have a different quality. But since these are both at the same temperature and on that same isotherm line, the value of HF and Fg will be the same for 3 and 2. The quality will be different. Now, if they give you, say, the volume, the specific volume instead, we can use that to find the quality. So there's other ways to find the quality here. So, as long as they give us 2 properties, we can find other properties at that particular state. Okay? So hopefully that gives you some ideas how you can calculate various work heats, and if you need to find if this is a power cycle because we're going in the clockwise position, the thermal efficiency, we can find those terms here. Okay?